One of the pillars of this channel is portable battery and solar power for field communication, self-reliance, and preparedness. So the amount of effort, the amount of time we spend on DIY builds and engineering new solutions is something viewers of this channel have come to expect. But since there's no one-size-fits-all solution for every scenario, we need to keep stepping up the game. So today we're building the most advanced DIY portable solar generator you've seen on YouTube to date. Today's build is a 12-volt, 576 watt-hour lithium iron phosphate solar generator. Alright guys, let's get started.
You are listening to the Emergency Broadcast Systems. This station broadcasts emergency news and official information on the air for a assigned area.
There's lots of information to cover in this video, so we're going to go through the specs and then jump right into the build. So the battery storage capacity on this solar generator is 45,000 milliamp hours. That's 45 amp hours or 576 watt hours. We're going to set up the cells in 4S3P configuration. That's 12 cells, and we're using the headway 15 amp hour cells. In this configuration, we could potentially pull 450 amps out of the pack. That's current amps load out of the pack. So you could start your car with it or your diesel locomotive. It's up to you. We're going to throttle back that current potential through the BMS to 60 amps continuous or 30 amps through the fuse block. Supporting this build is the Bestech BMS. That's the same BMS we used in the original 10 amp hour, 50 amp current load build earlier in 2018. We'll be using a K9 JEB distribution block. We'll be using the Genasun charge controller. Of course, you can use whatever charge controller you like. We're going to be using a wireless current shunt so that we can get the battery state and all the information about the solar generator wirelessly on our mobile phone. And we're going to be using a couple of 30 amp relays. To get power out of the system, we're using Anderson Powerpoles. Those are 30 amp fused, and we'll have up to 7 of them plus 2 USB outputs. We stick with Anderson Powerpoles for the solar input. We have 2 and they're wired in parallel. This will give us 140 watts of input. Now just to be clear here, this solar generator is an absolute monster. Actually, the battery pack, the heart of it, is an absolute monster. If this is your first build, I would suggest you go back to my first 10 amp hour, 50 amp load build and start with that one. For the rest of you, let's go ahead and get started. The very first thing we're going to do is create sets of 3 from our batteries. So I've started off with brand new cells from Headway. So these cells were manufactured around the same time. They have a nearly identical voltage, internal resistance, and capacity measurement. We're going to put these cells in parallel groups of 3. Then we'll use the Turnigy charger to check their voltage, internal resistance, check out the batteries in general, and then initial charge. When all 4 of those sets have been charged up on my Turnigy, I'm going to go ahead and place them into the trays. I'll put them in the same sets of 3 that I charged with the Turnigy charger in the beginning. Unless for some reason I take this pack apart and reuse it, these parallel sets of cells will spend their lifetime together. Now before locking things down, make sure you double check that your sets are all in the same orientation. I can't stress enough how important it is to check and double check your cells. Just a reminder guys, bad things will happen if you get it wrong. Now when you're ordering your cells, don't forget to either make or buy bus bars. Now since I couldn't find bus bars for 3 cells in parallel, I'm going to use bus bars for 2 cells in parallel, but I'll overlap them or double them up so that we can use them with 3 in parallel. If you're going to buy your bus bars, make sure you buy pure copper bus bars with a nickel coating. And if you want to pull more amperage out of this pack than I am, you can go ahead and double them up. Double up every bus bar. Just remember, when you do that, you'll have to account for that in the screws you use for your cells. The next step is to mark the cell positions on the pack. Adding these reference points to the pack will go a long way to ensuring we don't make some silly mistake and short out our cells. This is also a good time to take a look at the wiring diagram for the balance leads on the BMS. This way we can go ahead and mark those reference points on the pack as well. We'll use these markings not only for the balance leads, but for connecting the bus bars as well. So let's go ahead and install the bus bars. I'm going to use a single layer of pure copper nickel coated bus bars. It's very important to pay attention to the order we install the bus bars in. If we install the wrong bus bar without having protected the inner cell next to it, we could short out the pack. Now here you see I'm protecting the bus bars from short circuit while working on the next set in the pack. Don't cut corners, guys. Use your vinyl tape or Kapton tape to protect the bus bars when you're working on the cells next to it. All of these little things we do add up to ensure we don't short out our cells and make some terrible mistake with the pack. The headway cells have a torque spec on the screws, so make sure you pay attention to that torque spec and not just hulk those screws down. Alright, let's continue with our bus bars. Okay, when we're done with this side, take a look, make sure there's nothing that's going to short out when you connect the pack on the opposite side. Then we can flip it over and take a look at what's required for the next set of bus bars. Now I'm going to say this in good fun, but it's a little serious as well. This is where bad things will happen if you're not paying attention. So please pay attention. Okay, first things first, we're going to protect the bus bars we're not working on from the bus bars we are working on. So go ahead and put your Kapton tape or vinyl tape on to protect them. I'm installing these bus bars over the marks I created on the pack earlier. And I'm using a 4-pole bus bar, but I'm overlapping it so that it works with the 3 cells in parallel. I always make sure to use 2 hands when I'm torquing down the bus bars. This is an additional step to ensure we don't short out the bus bar on the opposing set. And there we have it. So let's go ahead and measure the pack now to make sure we're getting the voltage out of it, which we expect. Based on my initial charge, I am expecting to see something between 13.3 and 13.5 volts here. This looks outstanding. I'll take it. Now let's connect up the balance leads. We're not going to connect the balance connector to the BMS. We're just going to take the end of the leads and connect them to the pack. The BMS we're using for this build has 4 balance leads. One is connected to the battery plus, the next is connected to battery 4, 3, 2, and 1. Battery minus is not connected. The link to the BMS we're using for this project can be found in the description and the episode notes. The very first thing I do is mark the balance lead connector so I know which side is battery minus. This just provides us with another reference point so we don't mix up our balance leads. So now go ahead and find the mark you placed on the balance lead connector. Remember, we're not going to connect the balance lead to the BMS while we're connecting these leads. Now find that first lead coming off of the mark and connect that to the positive side of your battery minus. That may sound a little confusing, but use the wiring diagram from a couple of minutes ago in the video as a reference. This lead is referenced as battery 1 in the wiring diagram. Once you've got the lead for battery 1 wired up, find the lead for battery 2. From the BMS perspective, it's the one right next to the one you've already connected. Now you can go ahead and find that location you've marked on the pack and connect it up. Now we're going to repeat that for battery 3 and battery 4. Remember, battery 4 and battery plus are on the same bus bar. While we do that, let's talk about modularity in this solar generator. So some of you have noticed we are building modules in the solar generator. One module is the storage module, and that's actually the battery. What we're working on now is battery management. We break the system down into modules for two reasons. First, to make it simpler to build, and second, so we learn about the system as we build it. Now we have all the balance leads on the pack, so we can start buttoning it up. One thing I like to do is use Kapton tape to protect the conductive surfaces of the pack. It won't hurt to take your time, do it right, and make sure it looks nice. This way, when you open up the enclosure, people are absolutely going to be blown away by the quality of your build. Okay, while we're installing the Kapton tape on the bus bars, let's talk a little bit about lithium iron phosphate cells. Lots of people like using lithium ion cells, but the reason I like lithium iron phosphate is they're not volatile. They're not going to explode, they're not going to burst into flames. About the worst thing that's going to happen is they're going to vent if you short circuit them. Now sometimes there is an argument made about lithium ion cells having a higher energy density, and that's true, but a lithium iron phosphate cell has a much longer lifetime. So essentially it's a trade-off. With lithium ion cells, we have higher energy density but a much shorter service life. With lithium iron phosphate cells, we have a lower energy density, but a much longer service life. Alright, so here's the battery module with the balance leads and Kapton tape. We can clean it up and make it look much better later on before we put it in the enclosure. Now we've already integrated the balance leads into the battery module, but now we need to integrate the BMS with the battery as well. In the 10 amp hour headway build we did last year, I showed everyone how to solder up this BMS. I'm not going to do that now. Instead, I'm going to show you all the connections, where they go, and what they're for. In addition to the balance leads we just installed, the BMS has two connections. The first connection is B-, and that goes to the negative side of your battery. The other side goes to our fuse block and accessories we'd like to power. That's also where our charge controller comes in. Now we also have an additional but optional component in the system, and that's the wireless shunt. This wireless shunt is going to tell us everything about our solar generator and the battery at all times, and it's going to do so wirelessly and display that information on our mobile phone screen. So the wireless shunt comes from a company called Thornwave Labs. You'll find a link in the description and the episode notes. Now because this is so awesome, I believe it deserves a video of its own, so I'll be doing a separate video on this wireless shunt as well. And before we put everything in the enclosure, we need to do a bench test. So at the moment, the solar generator is powering my laptop, my Yaesu FT891, my Raspberry Pi, and it's being charged up by the Genasun solar charge controller. The tablet is there to run the PowerMan app on Android. So our goal here is to stress test the system. And we're going to run JS8 call at 50 watts with the Yaesu FT891. And we're going to watch the readings from the wireless shunt on the solar generator in the middle of the screen on the PowerMan app running on the Android tablet. Looking at the left side of the screen, you see I'm outputting about 50 watts. And if you look at the PowerMan app, you see that I'm putting out about 11 or 12 amps. You can also see that the battery runtime is updated in real time. So when the radio stops transmitting, of course, our battery runtime will be updated again. I like having that runtime update constantly because it lets us know at a certain power level how much time we can operate with this solar generator. But now let's look what happens when I pull the battery out of the laptop and let the solar generator power the laptop directly from the Powerpole connector. We'll see our runtime drop down to about 8 hours. Now if I put the battery back in, that should increase to something more reasonable for this solar generator. By removing that laptop battery, we recognize the solar generator was just trickle charging the battery on the laptop. Without the laptop's battery, the solar generator is powering that laptop entirely. Now with the battery back in, we can see the runtime go back up to about 1 day, 24 hours, 25 hours, which is respectable for 50 watts, transmitting every 15 minutes with the radio constantly on receive. Absolutely outstanding. I'll take it. Surprisingly, there's an awful lot of haters on my channel who oppose the use of the BMS board. Well, if you've been around my channel for any length of time, you already understand that all of my battery builds are built around a quality BMS. So for the BMS haters, here's a few reasons why we should use the BMS. First of all, we get high voltage protection, we get low voltage protection, and we get short circuit protection, and of course we balance the cells. Well, the haters are going to ask, well, why don't we simply bottom balance? And the answer is because bottom balancing doesn't offer us high and low voltage protection. It doesn't offer us short circuit protection, and it doesn't do anything for protecting our cells. So this is the 4S Best Tech BMS for lithium iron phosphate cells. This is the same BMS we used for the original headweight build. So based on the comments in the video from builders as well as myself, we've had really good luck with this board. We've also been able to secure a distributor from the United States who's giving us free shipping and ships pretty fast, so none of this waiting for 6 months from China for something to arrive. Now, because we're installing this BMS and the cells in an enclosure to become a solar generator, I wanted to encapsulate the BMS in some sort of structure to let it breathe, but to protect it from knocks and bangs and things like that. Now, you all can laugh all you'd like, I'll take it, and leave me your feedback in the comments, but I decided to use a couple of cutting boards to secure the BMS in front of the pack. I'm sure some of you clever 3D printing guys could print up something like this, and if you do, please reach out and we'll share it on the channel. But for now, this was the cheapest, easiest way to protect the BMS inside the enclosure with the cells. So the enclosure for the BMS also works as a stable mounting platform for the distribution board. We'll talk more about the distribution board a little bit later on in the video. So the idea of sandwiching the BMS between these two boards was allowing it to breathe and protecting it at the same time. With the first video we did with the 50 amp headway build, actually I used some heat shrink tape over the BMS to protect it, and I got a lot of feedback saying, hey, come on, if the BMS heats up, it can't breathe because of the heat shrink. That was absolutely true, and well, we had to come up with a better way of doing it this time. So go ahead and laugh if you want to, guys, but it's cheap and it works. While we're doing this, let's talk a little bit about who would want to use this or build this solar generator. Well, the battery box builders, the solar generator builders who can't afford to buy a commercial option or want a better option than the commercial solar generators offer. There's a lot of solar generators on YouTube, DIY solar generators on YouTube, but many of them are built with lead-acid batteries or cheap Chinese parts that really haven't been tested, and they're built with the sole purpose of being cheap, not being reliable for the long term. So for someone needing off-grid power in the field for an extended period of time, I think a 12-volt solar generator based on lithium iron phosphate cells is a good option. The closest thing that comes to it on the market right now is the Goal Zero Yeti 400. If we exclude the shunt and use a normal wired battery monitor, this solar generator actually outperforms the Yeti 400 but comes in about $100 cheaper. We also have the benefit of deciding what type of inputs and outputs we're going to use, as well as the solar charge controller we're going to use for the build. I think the most important aspect of building this DIY solar generator ourselves is knowing how to repair it or rebuild it or re-engineer it if it outgrows us or if it ever develops some sort of problem. With commercial options, they're almost never designed to be repaired. You use it, you throw it away, and you start again with a new one. Your investment is burned. Okay, so the BMS is inside the enclosure now. We have the battery minus as well as the power minus coming off the BMS board, and we can start making those connections. Now, I know a lot of you are going to start freaking out with these connections. There's seemingly a lot of them, but I've already gone through the video and shown you what each of them is used for. So there's no need to start freaking out. Pay attention and we'll get it all squared away. So for those of you paying attention, I'm now installing the positive wire to the battery pack. So the positive wire from the charge and discharge side of the BMS goes directly to the positive side of the cells. The battery negative side of the BMS is connected to the negative side of the pack. This should all be starting to make sense now. If it doesn't, watch the video a couple of times through and it'll start to make sense for sure. Now we're going to connect up the power and ground for the wireless shunt. These two connections will power the Thornwave power mon, as well as allow it to measure voltage. Now I didn't capture it in the video, but I'm installing a switch between the positive lead of the power mon and the positive lead on the pack. This will allow me to turn it off when I'm not using the solar generator or it's not being used for a long period of time. Now I've split the wire on the power side of the BMS so that I could do maintenance on the BMS if ever necessary. That's what we're doing in the video right now. We're going to connect up those two wires and then cover them with tape. Again, this is just a nice mod to make for maintenance or for making maintenance easier. Now I'm going to use some tape to secure the enclosure for the BMS to the completed battery pack. This will make it a lot easier to handle them both when we're installing them in the enclosure. Now before we start planning out and cutting into the enclosure, let's take a look at the K9 Joliet Echo Bravo distribution board. I've done a couple of small modifications to this to make it compatible with my requirements for the solar generator. So as you see, we have 7 outputs and they're all fused. The main input is also fused. There's also a pass-through port to run voltage to another device. The main input has 2 indicators, one to tell you power's on and the other to tell you the fuse is blown. The other 7 ports also have their own fuses as well as blown fuse indicators. There's also a dedicated port for USB, but I'm not using that. Now, just to be clear, without making any modifications, we can also use a fuse block for automotive or boats like we see in the upper right-hand corner of the screen. I may replace the distribution board with that automotive fuse block if I can find one small enough. But only because the automotive fuse block maxes out at 100 amps, so it exceeds the specs of the solar generator current draw we're expecting, which is a maximum of 50 to 60 amps. I'll leave information for both of these in the description and the episode notes. Now, with the exception of the wires, it looks like the battery module is pretty much ready to be integrated into the enclosure. So up to this point in the video, we've put the cells together, we've charged them up, we've integrated the balance leads, we've integrated the wireless shunt, and we've encapsulated and wired up the BMS. That means it's time to test fit the battery pack inside the enclosure so we can start doing some cuts for all the ports. So here's the ammo can we're using for the project. It's not actually the one I had hoped to use, but it's a good one nonetheless. It's available from Amazon and eBay, and it's pretty cheap. You'll find all the information about it and links to buy it in the episode notes. This ammo can is only slightly larger than the previous ammo can we were using on this build. But the elongated cover on this ammo can gives us a place to put our solar charge controller. In fact, you'll be pretty surprised about what we can actually fit inside this enclosure. Anyway, let's sit the battery module inside the enclosure so we can get some general idea about where we're going to make the cuts in the enclosure for the Powerpole ports. At first glance, I was pretty worried that I wouldn't be able to fit everything inside, but we have the battery module in there, we have the shunt in there. The only thing missing at this point are the ports, the switches, and the solar charge controller. And the Powerpole distribution block. Now, the downside of using this case is it's not entirely waterproof. That might be a downside for you all as well, but for transportation, I'm going to put this inside of a dry bag. That should solve the problem. Anyway, I took some measurements and I did a general layout, and now I can start fitting the ports for the enclosure. Let's get started by temporarily putting the backing plate on so we can make the marking for the Powerpole ports. If we jump forward in time here for a second, we can see why the placement of those ports was critical. The wires coming from the Powerpole distribution board don't leave a whole lot of room for the ports. So we need to place the Powerpole distribution board as high as possible, as well as leaving room underneath it for these backing plate and ports. All I'm doing now is making the holes that I'm going to make in the enclosure. I'll go ahead and remove the backing plate for the Powerpole ports, and I'll use my step bit to drill out these holes. Now I can go ahead and put the backing plate back on and start to insert the Powerpole ports. As with all the other components in the project, I've left links in the episode notes where to find these Powerpole ports. Now, while we're doing this, let's talk a little bit about my Powerpole port configuration. Now, first of all, there isn't any one right way to deploy Powerpole ports. I know that Aries, Races, Raynet, and other emergency communications organizations around the world have their preferred method of doing it. But my group also has its preferred method of doing it, and I deploy them in that way. Anyway, I do like the Powerpole ports from Anderson, but I'm also thinking that if I wasn't interested in emergency communications, maybe I would also use the XT60 or XT90 connectors. The XT60 and XT90 connectors are waterproof, cheaper, easier to find, and a lot more popular around the globe than these Anderson power poles. So the only reason I'm using the Anderson power poles is because of this standard in the amateur radio community. The bottom line is the Anderson power poles are actually inferior to the XT60 and XT90. So if you have the freedom to use them, you should know that there are also panel mounts for the XT60 and XT90, just like there are for the Anderson power poles. It's a lot more cost effective as well. So now we're installing this dual USB port from PowerWorks. Now, let's take a moment to talk about this one, and I'll actually show you an alternative I found. So the image on the left is a dual USB port with voltage meter I found on Amazon. So I'm using that one in another project, but it's important to point out that it's just as RF quiet as the PowerWorks version, and it has the voltage display. It's also more economical than the PowerWorks version. I'll leave links to the PowerWorks dual USB port as well as this Qualcomm 3 USB port in the episode notes. And here we are. The PowerPod actually fits very well with this enclosure, and I'm quite happy with how it looks. I think we can go ahead and install the solar input for the enclosure now. So we're going to do it in exactly the same way. We'll temporarily put our template on, we'll make the marking, then use our step bit to make the hole for the Powerpole ports. It's actually a pretty easy process if you have the right tools. So the 4 ports and 2 USB outputs with 2 solar inputs is actually quite enough on this enclosure for this solar generator. I have left some space at the lower right side of the enclosure so that I can add a port to it later on. I'm thinking I might add a high output port for an inverter if I ever use one. Alright, so these dust covers are actually just that. They're dust covers. They'll stop dust, they'll stop water splashing inside the connectors, but they're not waterproof. Although some channels are telling you that they are, they're absolutely not. But they're good for our application. Now's a good time to start integrating the distribution board and fuse block into the enclosure. So I've already taken the liberty of building up the distribution board. I used 45 amp Powerpole connectors on 10 gauge wire. This will help minimize losses and reduce heat in the system. I had to modify the distribution board to fit the 10 gauge wire, so I would suggest you use 12 gauge wire because that fits without any modification. If you have your heart set on 10 gauge wire, you can go ahead and use the automotive fuse block I showed you earlier. So once we're done installing our connectors, we can put those wires into groups. As you see here, I've made 2 groups of 4 wires. That's 1 group for each of the Powerpole connectors. The easiest way to do it was to pass those connectors through the hole in the enclosure and then plug them into the Powerpole ports. Don't forget to pass your wires through the locking ring before you connect those wires to the ports. Now, I mentioned earlier that I'm going to have 2 parallel ports for the solar input. So we need to make a custom cable for that parallel input. Here I'm using 14 gauge wire with 45 amp Powerpole connectors because that's what I had on hand. I don't expect to get more than 10 to 15 amps solar input from my panels, so the 14 gauge wire is fine for that. So basically we're making a single cable to go from the Powerpole solar input to the charge controller, but we're going to split that solar input at the cable and make a jumper to go to the second Powerpole port. Now you can see how we've just split that wire and jumped it over to the other port. Now I may upgrade this to 12 gauge wire if I ever plan on having a larger solar array. Anyway, for now we'll just push that cable through the hole in the enclosure and seal up the Powerpole port. Don't forget to run that cable through the locking ring for the Powerpole port. So the last thing we do is reinstall that locking ring. This will seat the Powerpole port onto the enclosure. So let's take a few seconds to have a look at how the enclosure looks with the Powerpole connectors, the wires, and everything else integrated into it. So as a prototype goes, I'm quite happy about how these ports turned out, especially the 10 gauge wires with 45 amp connectors and the Powerpole pods. Anyway, now it's time to do some testing. We should check to make sure all of our ports are working before moving forward. I've got one of my small DIY battery packs connected to the Powerpole distribution board just to get power to the ports for testing. If all the ports are working fine, we'll go ahead and do a test run with the solar generator's battery. These short tests are really just module testing to make sure each port is connected properly. We're going to do some brutality testing later on with the Yaesu FT891. Outstanding. We have good consistent voltage on every Powerpole port. Now let's test that USB port. Now, I'm fairly certain you won't see the charging light on this lamp, but I assure you it's working. Now let's try it with the tablet, and you'll definitely be able to hear when I plug the USB port into the tablet. Outstanding. The next step is to install the battery and battery management modules into the enclosure. Before you reach this step, you need to make sure that all your cables are solid. I mean, there can't be any weak link in your cabling. Anyway, you can see how all of the different modules are coming together now. In fact, it's at this point that you can probably notice the enclosure is actually one module in the system as well. Another module is power distribution. Now, building up this system module by module helps us to understand how to repair it if we ever come to a point where something is failing, or, for example, if we want to upgrade it. From a preparedness perspective, this is the strength over this type of build over a commercial solar generator like the Goal Zero Yetis. All right, let's keep moving forward. Mind those wires before pushing it in. Don't force the battery module into the enclosure. It should slide in with a little bit of guiding. Now, I'm not going to edit out this part of the video because I want you to see that I also have to remove the battery, get the cables out of the way before sliding it in, as you see now. But once all those cables are out of the way and they're nice and squared away, the entire battery module will slide perfectly inside the enclosure. So this is what the entire system looks like with all the modules integrated inside the enclosure. We have the battery module, we have the battery management module, we have the power distribution module, and of course the enclosure. At this point, the only thing missing are the switches, the relay, and the solar charge controller. Anyway, all of the hard work is done now. Now this video is definitely long enough, but what do you say if we go ahead and have a quick overview of what we've done, what we've accomplished in this video, and then start to close it down. So let's take a look at all the components we used to build this system. We've got an ammo can, we've got a MPPT charge controller, we've got the 15 amp hour headway cells we used to build a 45 amp hour pack. We have a battery management system, the Powerpole distribution board, we've got Anderson Powerpole ports, we've got the Anderson USB ports, and we have a wireless shunt delivering all the information about our battery pack to our mobile phone. By using lithium iron phosphate cells, we have 576 watt-hours of onboard storage. If you limit our discharge to 90% of capacity, we still have more usable power than lead-acid batteries, and we have a longer service life than other lithium chemistries. So we've taken the battery management system and the Bluetooth shunt to create a very unlikely partnership. Not only can we get information about our solar generator to our mobile phone, we could also get information from the wireless shunt to a device like a Raspberry Pi. I've never seen this functionality in a portable solar generator. The solar generator also isn't picky about the power source. We can charge it with our solar panels. We can charge it in the field with a portable solar channel, or we could use a pedal generator to top it up when there's no other solution for doing so. Please forgive me if I get ahead of myself, but it really seems we have something special here, guys. From where I'm sitting, it appears we've taken the DIY battery box and the DIY solar generator to an entirely new level. So are you ready to see it, guys? Well, here it is. This is our 12-volt lithium iron phosphate, 45 amp hour, 45,000 milliamp hour, or 576 watt hour DIY solar generator. So the best way to demonstrate this system is to show you how I'm actually using it here at home. So we're definitely going to get out into the field with this system, but for now that needs to wait for another video. But this is what I'm doing with the system. So at the moment, all of these devices are connected to the solar generator, starting with this Kenwood TMD700. It's powering the Yaesu FT891 and the Raspberry Pi running JS8 Call. It's also powering the tablet which we're using as a wireless screen for the Raspberry Pi and the Yaesu FT891. And if that wasn't enough, the Yaesu FT817 is also being powered, and I'm listening to my favorite radio station, Järvi Radio here in Finland. When we started this project, we wanted to find the balance between portability, battery storage and capacity, and the amount of gear we could actually power with it. So I think we can close down this video by doing a side-by-side demonstration of the Goal Zero Yeti 400 specifications and the specs of our DIY 12-volt lithium iron phosphate solar generator. Starting with capacity, the Goal Zero has 428 watt-hours at 10.8 volts. Our DIY solar generator has 576 watt-hours at 12.8 volts. You'll be replacing those batteries in the Goal Zero after 500 cycles, while that's 2,000 cycles for our DIY solar generator. This is directly related to the cells used to build the generator. On the Goal Zero, it's lithium ion, and on our DIY solar generator, it's lithium iron phosphate. The Goal Zero weighs in at 16.3 pounds or 7.4 kilograms. The DIY solar generator is 18.3 pounds or 8.3 kilograms. The Goal Zero has 2 DC output ports capped at 10 amps and 3 USB ports. It also has 2 AC ports. The DIY solar generator has 4 Powerpole ports at 30 amps and 2 USB ports. The max solar input on the Goal Zero is 120 watts. Max solar on the DIY solar generator is 120 watts. Charge controller on the Goal Zero is PWM, noisy, noisy, noisy. Charge controller on the DIY version is MPPT. I should also add the DIY solar generator came in at about $100 less to build it ourselves. So as you see, guys, it is possible to build your own DIY solar generator for less money but better specs than the commercial variants on the market. So the last thing you'll need to know is, where can you find the information? The first place to start is the description of this video. There you'll find a link to the episode notes. There's an entire breakdown of everything we've done to build up this solar generator on my blog, oh8stn.org. That includes links to all the products used to build this video. It includes all of the detailed information for each component and how we configured it, and so on. If you have detailed questions about building this solar generator, or you're stuck with something during the build, leave those questions in the comments. If you want a really fast, detailed answer, you can always join my Patreon community, or drop a buck in the tip jar and attach a note to it. If you're supporting the channel through Patreon, PayPal, or simply sharing my content, you're absolutely magnificent, and I couldn't do it without you. For the rest of you, if you like what I'm doing, if you like the content I'm creating, consider leaving me a comment and a thumbs up to let me know. And if it's not too much to ask, share this video with someone or someplace where other operators might enjoy it. Rock and roll, guys. Thanks for watching. Ciao.